dbus is an inter-process communication and remote procedure call mechanism that allows communication between multiple computer programs concurrently running on the same machine. dbus was designed as part of the effort to the freedesktop.org project to standardize services provided by Linux desktop environments such as GNOME and KDE. The freedesktop.org project also developed a free and open-source software library called libdbus, as a reference implementation of the specification. This library is often confused with the dbus itself. Other implementations of dbus also exist, such as GDBus, QtDBus, dbus-java and sdbus. Overview: dbus is an IPC mechanism initially designed to replace the software component communication systems used by GNOME and KDE Linux desktop environments. The components of these desktop environments are normally distributed in many processes, each one providing only a few usually only a Euro service. These services may be used by regular client applications or by other components of the desktop environment to perform their tasks. Due to the large number of processes involved, adding up processes providing the services and clients accessing them, establishing one-to-one IPC communications between all of them is an inefficient and quite unreliable approach. Instead, dbus provides an abstraction called bus that gathers all the communications between a group of processes over a single shared virtual channel. Processes connected to a bus don't know how it is internally implemented, but dbus specification guarantees that every process connected to the bus is able to communicate with each other through it. Linux desktop environments take advantage of the dbus facilities by instancing not one bus but many, a single system bus, available to all users and processes of the system, that provides access to system services. A session bus for each user login session, that provides desktop services to user applications in the same desktop session, and allows the integration of the desktop session as a whole. A process can connect to any number of buses, provided that it has granted access to them. In practice, this means that any user process can connect to the system bus and to its current session bus, but not to another user's session buses, or even to a different session bus owned by the same user. The latter restriction may change in the future if all user sessions are combined into a single one-user bus. dbus provides additional or simplifies existing functionality to the applications, including information sharing, modularity and privilege separation. For example, information on an incoming voice call received through Bluetooth or Skype can be propagated and interpreted by any currently running music player, which can react by muting the volume or pausing playback until the call is finished. dbus can also be used as a framework to integrate different components of an user application. For instance, an Office suite can communicate through the session bus to share data between the word processor and the spreadsheet. dbus specification =bus model every connection to a bus is identified in the context of dbus by what is called a bus name. A bus name consists of two or more dot-separated strings of letters, digits, dashes, and underscores. An example of a valid bus name is org free desktop. Network manager. When a process sets up a connection to a bus, the bus assigns to the connection a special bus name called unique connection name. This type of bus names are immutable it's guaranteed they won't change as long as the connection exists and, more importantly, they can't be reused during the bus lifetime. This means that no other connection to that bus will ever have assigned such unique connection name, even if the same process closes down the connection to the bus and creates a new one. Unique connection names are easily recognizable because they start with the otherwise forbidden character. An example of a unique connection name is 1.1553. A process can ask for additional bus names for its connection, provided that any requested name is not already being used by another connection to the bus. In dbus parlance, when a bus name is assigned to a connection, it is said the connection owns the bus name. In that sense, a bus name can't be owned by two connections at the same time, but, unlike unique connection names, these names can be reused if they are available. A process may reclaim a bus name released purposely or not by another process. The idea behind these additional bus names, commonly called well-known names, is to provide a way to refer to a service using a pre-arranged bus name. For instance, the service that reports the current time and date in the system bus lies in the process whose connection owns the org-free desktop timeUdate1 bus name, regardless of which process is it. Object model equals, because its original conception as a replacement of several component-oriented communication systems, dbus shares with its predecessors an object model in which to express the semantics of the communications between clients and services. The terms used in the dbus object model mimics those used by some object-oriented programming languages. That doesn't mean that dbus is somehow limited to OOP languages. In fact, the most used implementation is written in C, a procedural programming language. In dbus, a process offers its services exposing objects. These objects have methods that can be invoked, and signals that the object can emit. Methods and signals are collectively referred as the members of the object. Any client connected to the bus can interact with an object by using its methods, making requests or commanding the object to perform actions. For instance, an object representing a time service can be queried by a client using a method that returns the current date and time. A client can also listen to signals that an object emits when its state changes due to certain events, usually related to the underlying service. An example would be when a service that manages hardware devices such as USB or networked relays signals a new hardware device added event. Clients should instruct the bus that they are interested in receiving certain signals from a particular object, since a dbus bus only passes signals to those processes with a registered interest in them. A process connected to a dbus bus can request it to export as many dbus objects as it wants. Each object is identified by an object path, a string of numbers, letters and underscores separated and prefixed by the / character, called that because of their resemblance to Unix file system paths. The object path is selected by the requesting process, and must be unique in the context of that bus connection. An example of a valid object path is GDBus. However, it's not enforced but also not discouraged to form hierarchies within object paths. The particular naming convention for the objects of a service is entirely up to the developers of such service, but many developers choose to namespace them using the reserved domain name of the project as a prefix. Every object is inextricably associated to the particular bus connection where it was exported, and, from the dbus point of view, only lives in the context of such connection. Therefore, in order to be able to use a certain service, a client must indicate not only the object path providing the desired service, but also the bus name under which the service process is connected to the bus. This in turn allows that several processes connected to the bus can export different objects with identical object paths unambiguously. Members methods and signals that can be used with an object are specified by an interface. An interface is a set of declarations of methods and signals identified by a dot-separated name resembling the Java language interface's notation. An example of a valid interface name is org-free desktop. Introspectable. Despite their similarity, interface names and bus names should not be mistaken. A dbus object can implement several interfaces, but at least must implement one, providing support for every method and signal defined by it. The combination of all interfaces implemented by an object is called the object type. When using an object, it's a good practice for the client process to provide the member's interface name besides the member's name, but is only mandatory when there is an ambiguity caused by duplicated member names available from different interfaces implemented by the object. Otherwise, the selected member is undefined or erroneous. An emitted signal, on the other hand, must always indicate to which interface it belongs. The dbus specification also defines several standard interfaces that objects may want to implement in addition to its own interfaces. Although technically optional, most dbus service developers choose to support them in their exported objects since they offer important additional features to dbus clients, such as introspection. These standard interfaces are, org-free desktop bus peer, provides a way to test if a dbus connection is alive. Org-free desktop bus. Introspectable, provides an introspection mechanism by which a client process can get in runtime a description of the interfaces, methods and signals that the object implements. Org-free desktop bus. Properties, allows a dbus object to expose the underlying native object properties or attributes, or simulate them if it doesn't exist. Org-free desktop bus. Object Manager, when a dbus service arranges its objects hierarchically, this interface provides a way to query an object about all sub-objects under its path, as well as their interfaces and properties, using a single method call. Communications model. dbus was conceived as a generic, high-level inter-process communication system. To accomplish such goals, dbus communications are based on the exchange of messages between processes instead of raw bytes. dbus messages are high-level discrete items that a process can send through the bus to another connected process. Messages have a well-defined structure, even the types of the data carried in their payload are defined, allowing the bus to validate them and to reject any ill-formed message. In this regard, dbus is closer to an APC mechanism than to a classic IPC mechanism, with its own type definition system and its own marshalling. The bus supports two modes of interchanging messages between a client and a service process: one-to-one request-response. This is the way for a client to invoke an object's method. The client sends a message to the service process exporting the object, and this, in turn, replies with a message back to the client process. The message sent by the client must contain the object path, the name of the invoked method and, if it's required, the values of the input parameters as defined by the object's selected interface. The reply message carries the result of the request, including the values of the output parameters returned by the object's method invocation, or exception information if there was an error. Publish-subscribe. This is the way for an object to announce the occurrence of a signal to the interested parties. The object's service process broadcasts a message that the bus manages to pass only to the connected clients subscribed to the object's signal. The message carries the object path, the name of the signal, the interface to which the signal belongs to, and also the values of the signal's parameters if there is any. The communication is one-way. There are no response messages to the original message from any client process since the sender doesn't know who or how many recipients are. Internals. Most existing dbus implementations follow the architecture of the reference implementation. This architecture consists of two main components: a point-to-point communications library that implements the dbus wire protocol in order to exchange messages between two processes. In the reference implementation, this library is libdbus. In other implementations, libdbus may be wrapped by another higher-level library, or entirely replaced by a different standalone implementation that serves the same purpose. A special daemon process that plays the bus role and to which the rest of the processes connect using any dbus point-to-point communications library. This process is also known as the message bus daemon, since it is responsible for routing messages from any process connected to the bus to another. In the reference implementation, this role is performed by dbus daemon, and so it is in all other implementations since no one has developed an alternative. Dbus daemon itself is built on top of libdbus. Adoption. Heavily influenced by the DCOP system used by versions 2 and 3 of KDE, dbus has replaced DCOP in the KDE 4 release. An implementation of dbus supports most POSIX operating systems, and a port for Windows exists. It is used by Qt4 and GNOME. In GNOME it has gradually replaced most parts of the earlier bonobo mechanism. It is also used by XFCE. The usage of dbus is steadily expanding beyond the initial scope of desktop environments to cover an increasing amount of system services. For instance, Network Manager Network Daemon, BlueZ Bluetooth Stack and Pulse Audio Sound Server use dbus to provide part or all of its services, and Systemd is promoting traditional system daemons to dbus services, such as libdbus. It is also used as the wire protocol for the all-join protocol for home automation. To this end, all-join adds discovery, session management, security, header compression, embedded device support and makes it transport agnostic. Implementations: libdbus, Although there are several implementations of dbus, the most widely used is the reference implementation libdbus, developed by the same freedesktop.org project that designed the specification. However, libdbus is a low-level implementation that was never meant to be used directly by application developers, but as a reference guide for other re-implementations of dbus. The freedesktop.org project itself recommends applications authors to use one of the higher-level bindings or implementations instead. The predominance of libdbus as the most used dbus implementation caused the terms dbus and libdbus to be often used interchangeably, leading to confusion. GDBus is an implementation of dbus based on GIO streams included in glib, aiming to be used by GTK+, and GNOME GDBus is not a wrapper of libdbus, but a complete and independent re-implementation of the dbus specification and protocol. QtDBus is an implementation of dbus included in the Qt library since its version 4.2. This component is used by KDE applications, libraries and components to access the dbus services available in a system, SDBus. In 2013, the Systemd project rewrote libdbus in an effort to simplify the code, but it also resulted in a significant increase of the overall dbus performance. In preliminary benchmarks, BMW found that the Systemd's dbus library increased performance by 360%. As of version 221 of Systemd, the SDBus API has been declared stable. KDBus. There is an ongoing development project called QtDBus that aims to re-implement dbus as a kernel-mediated peer-to-peer inter-process communication mechanism. Beside performance improvements, QtDBus would have advantages arising from already existing Linux kernel features such as namespaces and auditing, security from the kernel mediating, closing race conditions, and allowing dbus to be used during boot and shutdown. QtDBus inclusion in the Linux kernel has proven controversial, and as of September 2015 has not been merged yet. Language bindings. Several programming language bindings for dbus has been developed, such as those for Java, C and Ruby. See also. References. External links. dbus homepage at freedesktop.org, dbus specification, introduction to dbus on the freedesktop.org wiki, dbus tutorial, dbus overview.